Okay, yeah. So, what am I going to talk about? So first, I want to talk about several kinds of groups supported by OSCAR, very similar to what Bettina said. So, thanks to her talks, I can do a lot of things quite quickly. And I just refer to how this is a gap. You know all this already. And OSCAR is quite similar. Then so something about attributes of groups and well, group libraries, resources of large collections of groups. If one wants to find some interesting groups, these libraries are a good thing to start at. Then important concepts, group actions, and G sets. We have already a little bit about that in previous talks. And then last concept, group homomorphisms. And along these lines, well, in another dimension, say, I want to explain some general concepts, how this is thought in OSCAR, what principles we have in OSCAR, or maybe even generally in Julia, which are behind. And then I want to show also some code examples to play with, well, perhaps a little bit more than in previous talk. So, okay, yeah. We have seen already in Max's talk, there is a documentation, OSCAR manual. And if we look at this, then we find under the groups section some introductory page which lists already what we have seen earlier. Yeah, we have permutation groups, matrix groups, finite representative groups, polycyclic groups. Now this is what will be topic in the next minutes of the talk. Yeah, as Max suggested already, well, yes, this is the address for the OSCAR manual. Make a bookmark, and then if you have general questions, look there. Many of much of the information which is not directly related to individual functions cannot be found in the Julia online help. Just here, so that's why it's quite useful. If you are going to the Julia session itself, you started, you load OSCAR, using OSCAR. Then we have seen already there is this help mode. You type a question mark, then you go to help mode, and then you can, if you know how the function is called, perhaps from the manual, perhaps from guessing, then you can get information about such a function by entering the name, and then usually one will get some description of what the function returns, what the arguments are expected to be, and then, well, if you're lucky, also some examples to play with. Concerning the name of the function, so one rule of thumb is that well, most of these function names, they are lowercase, and then different words are just joined by underscores. So in GAP, it's different. There we have words where the first letter is capitalized and there's no underscore in between. So like this is a general Julia habit to name functions like this. Okay, let's go to the first kind of groups, the permutation groups. So we have seen already symmetric group, the group of all permutations of a set of given cardinality, here 3, 5. And well, such a group we have seen, Bettina spoke, most of these groups, they have generators. So the function OSCAR for that is gens. And well, symmetric group has 2 generators, and we can assign names to the individual generators with this syntax. So Julia can return several objects at the same time. So gens is this array of with 2 entries, and here X is assigned the first entry and Y is assigned the second. Which can be quite handy. And well, we have a group. What can we do with a group? There is an identity element, which we get with the function 1. We can multiply group elements, so the group operation is always the infix multiplication, like gap, and the inverse can be computed with inf. So these are the operations for a group, and now we see if we take such permutations, we get also such permutations. They are printed in a way similar to gap does. And well, we have a symmetric group of degree 5, and all the elements in this group have degree 5. So also the element y, which swaps just 1 and 2 and fixes 3, 4, and 5, it still has degree 5 because it knows that it belongs to this symmetric group. That's different to what gap does. So there, the permutations don't know anything about a particular group to which they belong. Here, each such group element knows about its group, and we can get this as the value of the parent attribute. So most of the algebraic objects of elements in rings and fields and groups, they have such a parent, particular asking an element for its degree is a reasonable question. One can think of, well, if we multiply two elements with the same parent, then also the product naturally knows that it belongs to the same group. Whereas if we want to multiply permutations from different groups, we have a problem. And that's something that may work in special cases, and there is, for convenience, a possibility to do this. But in other cases where one would get a result in gap, in OSCAR, one might end up with an error message. So that's a little bit more restrictive. Okay, yeah, symmetric groups, they are just one special class of permutation groups. If we want to have general permutation groups, we can generate them, for example, by some given permutation. So we start in a symmetric group, and then we take, say, I want a permutation which swaps points 1 and 2. And then by calling the function g, so the symmetric group of it, we construct an element of this group g. So it's, I can think of embed the permutation required by this input into the group, and then we get a permutation which has parent this group. And then, okay, here I have written check equals false. In many cases, if we don't do this, such a constructor will be very careful. Is this permutation something which really lies in the group? And then, therefore, it performs a membership test. Well, if you know what you're doing, you can skip this membership test by writing this. If not, then it's better to have this check. But one has to keep in mind that, well, maybe this function coercing something into it, so embedding into a permutation group, this comes with some overhead. Okay, so now we have some element of symmetric group constructed explicitly from the way how it computes these integers. And now forming a subgroup of the symmetric group is done by the function sub. We have the symmetric group and then a list of these generators which we want. And then usually the functions which construct certain groups from another group, subgroups say, they come together with an embedding. So the result, we get first the subgroup which we want, and then some embedding with homomorphism from H to G. Okay. And then the subgroup G and H we have generated, well, we also have subgenerators, the ones which we were giving it. And well, this H, well, it has order 2. We can ask it for its properties, and well, it's just a group, a permutation group. It's not a symmetric group, but generated in a different way. So now this is already enough for doing some experiments. Suppose we have some cards for playing, 2 n cards, and we want to shuffle them. And one strategy for that is we cut this deck of cards into 2 halves, and then we merge these 2 halves again, and then we repeat this in order to get a random distribution. And with this strategy, we get well, essentially 2 generators of the group, which can be described by this. First we can merge them first. That the first card of the first deck remains the first, or it can be then the first card of the second half, which becomes the first. So now we have these first n elements. They can go to the odd positions, and the second leg goes to the even positions. That's permutation which we can get like this. Or we do it the other way around. The first half goes to the even positions, and the second half goes to the odd positions. Okay, the group which we generate like this can be created with these commands. We take, well, the odd positions. So this is a range which has a step size 2, goes from 1 to 2n minus 1. And these are the even positions from 2 to n. And if we put these two behind each other, then we get the permutation described by this rule. And doing it in the other way around, first the even positions as images, and then the odd positions as images. This gives us this permutation. So this way here we have two lists of integers. Now we take our symmetric group on 2 points and create a subgroup of the symmetric groups, which is obtained by taking the permutations described by these image lists. S of P1, S of P2. And then, as I said, sub returns the group and the embedding, and we are interested just in the first entry, the group, and this is returned. Okay, so this, we have a short OSCAR function which describes this group. Now let's see what exactly we are doing here. So for the case n equals 4, so this list of images which we obtain for the first commutation like this, that's what we wanted to see. Okay, and then if we then apply the symmetric group to this list, it gives us the commutation. So this is what's going on behind the scenes, what this function will do. And now, let's apply this function to n from 1 to 10. We construct this shuffle group and look at the order which this group has. So this is for 2 cards, 4 cards, 6 cards, and so on. These are the group orders. And well, if we compare this to the full symmetric group, these numbers look quite small. In particular, here for n equals 8, we got just a group of order 64. It's apparently not such a good strategy. But if we take such a deck of cards which one can buy in the shops, then 32 cards, this is then described by the shuffle group with argument 16. Well, these are the generators which we get. And the group order is 160. So we learn that the strategy to use these two permutations is a very bad strategy. It does not give us a really good way to shuffle cards. One has to think about better permutation. Okay, that's first example. So now Rubik's Cube, we have seen already last week in these introductions. We can regard it the underlying group as a permutation group on 48 points. If you just number all these little faces by the numbers 1 to 48. So that's something we need not discuss in detail. So here is the description how one would enter this in OSCAR. Again, take the symmetric group on 48 point and then the subgroup generated by the permutations given by these image lists. And so there is a very old gap advertisement session by Martin Schönert, which can be found in the web, and homologous OSCAR session can be found here in the list of exercises for later. There are links to these two sessions, so if one wants, one can play around with them. And there is even one exercise with a quite similar question to study a group by first entering it and then looking at some properties. So Rubik's Cube. Another permutation group, Lloyd's 15. There's such a puzzle. We have 4 by 4 entries, and then there is one empty place. And these numbers are usually not ordered. The aim is to order it, and the allowed moves are to move up or to the sides. This empty place. And then in the end, the empty place should be again in the lower right corner, and then the numbers 1, 2, 3, 4, and so on all the way. Also, question about permutation groups. So which permutations can one really realize with these moves. And in GAP, there is a function one can do this interactively. So what this Julia, or if you are at GAP, then just enter browse puzzle. One can play this puzzle. Okay, so permutation, good question. Okay, let's look at another experiment. We have seen it makes sense to ask for the number of fixed points of a permutation because it has a degree. Yeah? So the identity element of the symmetric group on 5 points has 5 fixed points. So now, what is the number of permutations in the symmetric group on n points which don't have fixed points? So if we want to compute this, we can proceed as follows. We take the symmetric group on n points. Well, write down the list of elements. Bettina has warned us not to do it, but well, we can do it. And then this set of elements, we filter out those which have 0 fixed points. Number of fixed points is 0. And then we ask for the length of this list. And well, in order to get a proportion, we divide by the order of the symmetric group. Well, that's a very easy function. And well, everybody will say, you can't do it like this. This is horrible. Don't list elements of the symmetric group. The first thing one could think about is, well, syntactically, that's not a very clever way. So without thinking about mathematics, one can say that, okay, you don't want to write down this list of elements, then filter it, and then ask for the length. We are interested just in a number. So there is a function counts, which describes the number of elements of something with respect to a certain property. So we can formulate this, make a symmetric group, and then with respect to the predicate, this element should have 0 fixed points. Well, count this and divide. That might be already better because, well, at least we need not write down all these elements at the same time. But of course, well, it's much better to use mathematics, to use some theory. You need not look at each individual element of the symmetric group. It's enough to look at representatives of conjugacy classes because conjugate permutations have the same number of fixed points. They have different fixed points, but same number of fixed points. So it suffices to look at the conjugacy classes, take for each representative, and then if it has 0 fixed points, then just add to this count the length of the conjugacy class. And then if we run over all the conjugacy classes, in the end, you get this number, and well, again, we have to divide by the order of the group. So that is more promising to be a better function. Okay, we have 3 candidates. Let's call them. First of all, well, where's 1, where's 2, where's 3 are the results. They are all equal. This is good. So at least we either we made a mistake in all 3 cases, or it's some evidence that they are doing the right thing. And yeah, next thing, this third function, which goes over conjugacy class representatives, this is much faster. It needs well, just about 16 milliseconds. And well, the other functions about 4 seconds. So well, this was expected. A little bit surprising that the second function, which we thought would be more nice for the system because, well, we asked for less, it's not faster. So we can really ask us what's the reason here. This example perhaps too small for being well suited for the second function, because on the other hand, there is some overhead for dealing this internally. We don't write down the list of elements, so we have to do something equivalent for that. Well, that's we could study this if we're interested in. That's another question. And yeah, the last thing which might be interesting is that, well, here we see for the third function there is 82% compilation time contained in this time which was used. So what does this mean? What do we do? well, we call this function 10 times, and then we create this list of results. And this is something which cannot be precompiled. So the function itself is compiled. It does not need compilation time and runtime. But the interpretation is, even this short time is dominated then by the efforts to create this result. So if we would put this into a function, we could get rid of that. But okay, that's we have to think about what we are really asking for. Yeah.
The second one seems to take less memory than the first one. Could it be that maybe it was more optimized for memory?
Yeah, this was the idea. So if we are thinking about if the group need not write down all its elements at the same time and put them into a list, but we can look at these elements one after the other, this is better suited for the memory management, say. Yeah? But well, as I said, we would have to study this if we are interested in it. Yeah, and so such questions arise if one wants to optimize codes, and then sometimes, well, one finds really funny reasons for effects which one did not think about before.
Okay. And you decided not to use count in the third program. You could have used count, but that has slowed it up. I mean,
Count.
You could have used count somewhere. You just did it with conjugacy classes.
Well, so I want to sum up the length of those conjugacy classes which fit.
One of the length.
So in this case, count does not help. Yeah? So, but it's of course it's important that I don't unpack the conjugacy class. I don't run over the elements. Just the conjugacy class knows its size, and then this is something which is expected to be cheap. Okay. Yeah. Okay. Now from 1 to 10, we can apply this, and this third function looks good. So let's do it from 1 to 10, 20, and we compute coordinates. Yeah? So for each number n, this proportion of fixed point free permutations. This is computed, and then we use function plots. And in order to apply this, first we have to load a Julia package called plots, which contains this function. This is not contained in OSCAR, so we have to load it in addition. And then we ask it to plot these coordinates, and well, not as an interpolated function, but just these points which we have measured. And then the result will be something like this. So if we do it in the Julia session, some window pops up which shows us this picture. So it starts here, and then all these values are very near to each other. This looks well, up to 20. We guess something like convergence. So let's zoom a little bit into this. So forget about this beginning and look what happens here behind. So let's take just the values from 6 to 20. Again, plot this. You get this. Here it starts here, and then again, they're very near to each other. So this really gives us the idea that they are coming closer and closer to each other. So let's look at what are the actual values there. So the last value, this is 0.36787, inverse 2.718281. So we have a guess what this limit could be. Well, yes. Okay. So let's take the difference with the exponential function at -1, and then we see this is already something 10 to the -17. So this is quite near. And then, do we need more evidence? So we have a conjecture what the limit is. We could think about, let's go up to bigger values of n. And if we want, then perhaps we have to rewrite the codes and perhaps forget completely about using symmetric groups, because all these are questions about partitions and some centralizer orders for given partitions. So this can be sped up a little bit if we want. And then in the end, well, can we prove it? But at least for the third point, OSCAR will not help. So OSCAR does not have approval for such conjectures. So it's something which you still have to do on your own. Okay, so that's the end of this example. And now also end of what I wanted to show about permutation groups. So the next step, matrix groups. Yeah, similar to the symmetric group, can create general linear groups here, 2 by 2 matrices of the finite field with 3 elements. Again, this has generators. Again, 2 generators. We have the identity element. We can form products. We can form inverses. Also, a matrix group has a degree. This is just the size of the matrices. And well, what we don't need in the case of permutation groups, the matrix group knows over which base ring these matrices lie. They are defined here over this contour of characteristic 3. And then again, well, as I said, also matrix group elements, they have a parent, and this is the group where they were constructed. So similar to permutation groups. And what one has to be careful about is to distinguish elements of a matrix group and matrices. So again, there is no such difference. Here we make a difference. So there is a function matrix which, let's say, unpacks the matrix group element and gives you back the raw matrix. So it prints itself in the same way as a matrix group element, but don't be confused. Important point is the matrix group element is not regarded as equal to corresponding matrix. Reason behind that is, well, one reason behind that is, well, for questions about linear algebra, like give me some solution for an equation system. This is something which is not defined for group elements. So for that, we would to go back to the matrices. On the other hand, doing something like give me the commutator of 2 elements, that's not defined for matrices, but for the group elements. One might even argue that, say, for matrices, commutator could be something like the D bracket or so, but well, it's not the case, but well, one would be free to define it like that, so it's not there. And perhaps what makes things then maybe a little bit more complicated for convenience, some operations are defined for both, and then sometimes maybe the function for group element may delegate to the functions for matrices. Determinant is such a function, and here one can argue that, well, determinant makes really sense for group elements. Determinant is even can be regarded as a homomorphism from matrix group to the base ring. So sometimes it works, and in other cases, one has to know one should go to one of the sides where it makes sense. Okay, and then again, can embed such a matrix and into the matrix group, so the other way around, take a matrix and then embed it into the group by calling this G as a structure for group element, and then the result is equal to the original element you started with. Okay, next kind of groups, finitely presented groups. We have seen starting point, or the most important cases are pre-groups. So then we construct the group with an appropriate command. We group here. Not really surprising that it is called like that. It has generators. These are these letters where one can create words. And so some group element maybe like this. We take some product of these generators, and this will be then an element of this group. Inverting means just reverse the word and invert all the letters. That's also an element of the free group. And in order to create them finitely presented groups, quotients of free groups, there is a function quo which takes the group, and then well, as we have seen, a list of elements in this free group, and then the result is the group which is the largest factor group that contains element kernel. Again, here quo returns both the factor group and the map from the free group to this factor group. Then for this finitely presented group, then one can ask questions. Here, for example, the square of the generators are trivial and the generator is null, and the result is the Klein-4 group. Okay, and then as we also have seen already, if we make the presentation a little bit more complicated, something like this, then questions become infinitely more complicated. And yeah, if we construct this and ask this quotient whether it is finite, we sit there and wait and wait and wait, and nothing happens. Yeah? So that's what we have learned already in the previous talks. Okay, yeah, because of these decidability questions, it's more experimenting. So that some people say that dealing with finitely presented groups is more art than science. Yeah, so okay. Polycyclically presented groups, Bettina has introduced and has explained them. So we have presentations, but in a very special form, such that all these elements have normal forms which can be substituted. For these groups, we have very good algorithms which are different for those for general finitely presented groups. Writing them down, especially creating them by hand, is quite technical. So one really has to know what one does. But once one has such a group or the possibility to get a presentation of this kind, then this is recommended for groups which have such a presentation. So why not solvable groups if one can do one? One should deal with polycyclic groups and then not with permutation groups. And well, many functions will automatically or naturally return such PC groups. For example, this small groups library, which we also have OSCAR, this returns whenever the group is solvable such a PC presentation, and then one works already with a recommended type of group. So before 12, order 24. I think this is S4. Yeah, so it's Christmas date. Yeah. So, okay. Yeah, so we have seen the important kinds of groups which we have, very similar to what we have in GAP. But on the other hand, there are details which are different in GAP and OSCAR. So one has to get used to some syntactic difference, but in principle, well, the mathematics behind is the same. And in many cases, also the functionality is the same in the sense that OSCAR relies on what GAP does for the computations. Yeah, well, groups for which properties, which attributes can one ask? Yeah, are they finite, abelian, solvable, simple, super solvable, whatever that's there? And the names are different from those in GAP, just one can guess how they are, so it should not be a problem. There are some numerical attributes like the order, which is size in GAP, exponent, the number of quantities, now go on. Subgroup construction, so you can ask for the center, the derived subgroup, for T subgroup, some Zulu subgroup, and then keep in mind it returns the subgroup together with embedding morphism. And well, forming quotients, there is, besides the general quo, for example, this maximal abelian quotient, so commutator factor group, I think, GAP, which returns then this factor also together with morphism. There are functions to return subgroup series, a derived series, a lower central series, upper central series. And there, okay, we have just an array of subgroups, no morphisms. If necessary, one can create this morphism afterwards if one needs them. Okay, group libraries. Yeah, well, some group libraries. There are more. There are some very small libraries. They're useful, but the most important ones are here. So permutation groups, which are transitive on a set of move points. So one up to the degree, and the degree can be at most 48. They are available. So you can access via the function transitive group. So for degree 12, number 295, this is the Mathieu group N12. And now for primitive permutation groups, so those which are transitive and where the point stabilizer is a maximal subgroup. Well, this is much more restrictive, this condition. So those are available for hardware degree. Also there, well, for degree 12, number 2 with N12, so it's also there, just at a different position. there's a library of perfect groups up to group order times 2 million. Yeah, of order 95,040, the first one. I think the only one is a catch-all. No, that is also a 12. And then, of course, these famous small groups, where small has, well, what is the meaning of small? So the order can be at most thousands. If the order is cube-free, one can go up to 50,000, and then there are some more series where the groups also are classified, and then in this sense they are counted as small. Maybe in the future, the meaning of small will change in this sense, that more classifications are available. So anyhow, here again, more group 24 to more. Okay, libraries. And all these libraries, they have a similar structure. How to access them, what kind of things one can expect from them. So there is usually a function which gives us for a given degree or for a given order, then the number of groups which are in this library. There is a function which allows us to get all those groups of a given degree or order, maybe with certain properties. So these are built in the sense that the system then does not first create all these groups of order 8 and then throw away all those which don't satisfy this condition, but has some pre-computed indices for fetching just those which are asked for. Also, even big numbers of groups, if one is able to restrict those to those which one is interested in to a very small subset, then this can be fast and also need just little memory. But one should look up in the documentation which such properties are supported with library. And this also might grow if people are interested in all such properties. Okay, yeah. That's okay. And another function which is usually available for these libraries is very important and very useful identification. So if a group can be found in the library, then it has a unique identifier, a unique label, let's say. For example, the symmetric group of 3 points has the identifier 6,1, so it's the first group of order 6 in this library. Well, a small group of this identifier is isomorphic to that, but it's of course it's returned as a PC group, so it's not equal to the group which one was giving. So it's the library classifies the group up to isomorphism, and for which way one can then perhaps even switch from one group which one was given to the one from the library, and then continue with that. Okay, libraries. And next is a concept about group actions. Well, sometimes one hears that groups are interesting just because they are acting on something. So a group action is an important concept. And what is an action? So well, we have a set, and we have a map that takes an element of this set together with a group element, and then the image of this set element under this group element is then again in the set. And well, this map describes this. And well, the map should have the property that well, mapping under a product of group elements should give the same result as first mapping under the first element and then the result under the second. And the identity should fix the set, each element in the set. So these are the rules of the game. And so whenever this is satisfied, we have a G action. And then there are, of course, a lot of natural actions. For example, for permutation groups, we take an integer, map it under a permutation, and it gives us another integer. Or we can take a vector of integers, map this under the permutation by a pointwise action on this entry of the vector. Or we could also say that if I have a set and I want to consider the action only up to ordering of the set, so I want to act on unordered sets, then I can regard this as an action. Conjugation in the group is also such a group action. So we can just apply group elements, group element, and that's like that. If we have a polynomial on n variables, and I take a permutation of these n integers, then I can act by permuting these variables. So permute the indeterminates, or more generally, I can take a polynomial and then I can act with a matrix, n by n matrix, by taking the linear action of the matrix on the determinates, and then evaluate this polynomial at the result, this linear combination. This also defines the action. Was also very simple. I take a vector, multiply it by the matrix group elements. Think of multiply the vector by the matrix and form the matrix group element given by the result. This gives us the group action there. Well, here the action function is not this caret, but for convenience it's multiplication, because it's matrix multiplication. We don't want to mix this up with computation. Or another example for that is if we take the right cosets subgroup, so G is an element in a group which contains H as a subgroup, then multiplying this with elements from the group G gives us another coset. At least again, the right coset is given by represented with G2. So this also defines group action. So in these cases, all this is predefined by these infix functions. Can apply it just like that. So this is somehow the default. And then there are also some custom actions like, we can act on vectors not necessarily containing integers, but anything, by permuting the positions in the vector, also by permutations. This can, of course, not be described by this function, because we know already what the image of a vector of integers under a permutation is. So it's something different. So for that, we introduce then some function which defines this group action. Okay. Action, and if we have such a group action, that this set together with the group and this function which defines the action, this is comprised into an object which is called a G set. That's something which is, it could have been supported in GAP, but apparently there was no feeling that it is needed. In OSCAR, we have decided that we want to create some G set objects which make explicit that we have the group, we have the set, we have this function. Similar way as we want to assign elements to a particular group, its parent, so it's more restrictive. So then it makes more sense to have this G set object. And then we can ask something like, okay, we construct this G set from the group under the, for given elements of the set, and then the elements of the G set are just the images of all these group elements, images of these seeds elements under the group, and somehow the closure under this group action. And here we could give also the function if needed, but here we don't need, because we know that if we are giving this vector of vectors, then it means an action in all pairs. So which is called on tuples in GAP. So once we have this G set, we can ask for the representative, give me one such element of the set, give me the orbit of one element in the set. It makes sense to ask for the stabilizer of some elements, or give me an element of group, if possible, which maps this element of the set to this one. And if not, then this function must have the possibility to return, that's not possible. Okay, we can ask whether the set is transitive, so all elements are in one orbit, whether it is primitive, for the sense of that transitive and the stabilizer maximum, or also the homomorphism induced by the set. So the permutation of the elements of the set, which is induced by this action, this will give us a permutation group. And moreover, mapping each element of the group to the corresponding induced permutation action, this defines the homomorph. For that. So this makes these objects interesting and well, sensible to deal with. Yeah, for example, here we take a symmetric field of 4 points, 0 to subgroup, and then have the action of the symmetric group on the right cosets of the to subgroup. This is set, and right cosets is a function which returns automatically such a G set. So it's the natural object associated to this mathematical notation. So it's definition, and then yeah, of course, here we ask whether this is primitive. Yes, it's true. It's clear that it's transitive, and the subgroup has index 3, so there cannot be any intermediate sum. Okay, that's one of these concepts which we provide. Now, some more example. We have seen symmetries are the main topic for the motivation for dealing with group and also let's look at the symmetries of a regular icosahedron. Here we are lucky. Somebody has already implemented in OSCAR platonic solids. That's something from the polyhedral geometry part. So we can just use it. We call this function, and then if we ask at the Julia session to visualize this, we get some picture. We have seen already similar picture before, and in the live session, this is even interactive, so we can rotate this with one ball. So fancy. Okay, so this is our icosahedron, and people who have implemented this platonic solid, they also provided a function of homomorphism group for that. So the symmetries are already available for us, so fine. Even if we call it, we get two such action, two permutation groups, one on the 12 vertices and one of the 20 faces of the icosahedron. And we first decide, okay, let's look at the action at this permutation group on the 12 vertices. That is a permutation group. It's isomorphic to the direct product of the cyclic group of order 2 and the alternating group 5 points. So here we have some generators. And let's say we are given the action on vertices and on faces, but maybe we are interested in the action on the edges. These are 30 edges of the icosahedron. How to get this? And if we let's go back, if we can trust the developers that they have written this permutation group in such a way that the numbers in permutation generators they correspond to the numbers here, then there should be an edge between 1 and 2. Let's take this edge 1 to 2, and then we form the orbit of this edge under the group. So we know how the group acts on Z's by default. It gives us, it maps each point, each endpoint of the sets under the permutation, and then forms the set of that. So that's the group action. So you get the orbit, and then we see, this is something which has already the right cardinality, 30. This is okay. This would give us then, if this assumption fits that 1, 2 is really an edge, then this would be already the result. And to get more evidence for that, let's look at those edges or elements in this orbit which have a 1 in, so everything which is connected to 1. And then we see this is 2 and 5 and 6 and 4 and 3. And if we want to go back, 5, 6, the 3 is behind, so this also fits. It looks good. So we could prove this, or we would have to construct it in another way. But this way, now we have constructed one operation from another operation just by using what we have seen and we can do with these group actions that G says. Yeah, question.
Sorry, am I lost? What's a group G? Is that?
G was the this automorphism group of the this platonic solid on the vertices of the group 12, and these are the generators. Yeah? So this is what we just took for granted, which was associated to this icosahedron forget from the system. Okay. Yeah, okay, and then once we have this, then we could look for what's the stabilizer of our original edge in the group, and then we see that okay, these are three generators. Well, this is the identity; it would not be needed, but here we have two generators. Well, one of them just swaps the edge, and the other one leaves all the endpoints of the edge fixed, and then if we go back, then I would see that one such stabilizing automorphism is just rotate it by half, and the other one is what is it? I think mirroring in the plane which contains this edge. Yeah? So these are something which one can study if one is interested in such question. Okay, now the last concept, group homomorphism. Yeah, for complete sake of completeness, what is a group homomorphism? We have map from a group to another group, and this map should respect the group law, so it should be it should compute with the group multiplication, and it should map the inverse of a group element to the image of the inverse. Okay, and defining group homomorphisms as objects for working with. There are several possibilities. So let's take some group, and then we define just a function, take this element of the group, and then return this element. So square each group element. That's something which works for all Abelian groups. So this defines the group homomorphism. Or another important and useful way is where we describe just images of the generators. That's enough for defining the homomorphism. And here we can just give them as a list. So it's the same homomorphism, just defined in a different way and a different object. So for each generator of the group, return its square. Yeah, so another syntax for creating such a group homomorphism. Or, can define, as we have seen, first a group action, G set, and then ask for the action homomorphism, which is given by this G set. This also gives us then homomorphism, and then can ask for the image of the homomorphism. Order. In this case, we start with the symmetric group at 4 points. You get an image of 24 elements. So this is then apparently an isomorphism we get. And the main idea behind group homomorphism is studying mapping elements to the images, computing pre-images if possible. So maybe there are elements in the codomain which don't have pre-images, and we want to get also the answer, no, it's not possible, or if possible, yes. And this is one pre-image. So these functions, they are available, pre-image or as pre-image with pre-image. And then asking for, is it injective, is it subjective? What is the kernel? If it is not an injective homomorphism, and then it can be set. Okay, that's all I wanted to talk about. Are there questions? Sure.
Is this all implemented in Julia, or is it powered back to?
Interesting question. So it depends. So originally, essentially all the group theory functionality was implemented by calling into gap. And well, meanwhile, there are situations where we see that something can be done better in plain Julia, and then we don't ask gap. But of course, this is in several cases complicated because maybe that calling gap would have some side effect that computes already some attribute which can be used later on. And if we do it in Julia, then this may be missing later on. So it's always a decision what is better. Say, if we introduce new functionality also, we can do it in Julia, and sometimes we can do it better in Julia. And for well, more importantly, perhaps, if we do it in Julia, then we have it directly there. If somebody asks for a certain feature, then it's quite inconvenient to say that, okay, we do it in gap, wait for a month or so, then we can have the new gap in OSCAR, and then you have this feature. So, but it really depends. Huh? So sometimes it's really beneficial to do it in Julia, and well, sometimes also for new features, we say that, okay, that's something which is very useful to have also in gap, and which we can then call from there, and then so both is possible. But it's still a lot of functionality comes from gap, and its packages, of course. So, and in individual situations, it's perhaps not even easy to explain which parts came just from gap and which not. The most important thing is that we get this functionality, of course. Bettina?
So it's the same question.
Yeah, same
In
answer.
particular, with the group libraries, I suppose that these are reference for.
Yeah. So for
big
group libraries,
yeah.
that's good. Well, and for group libraries, I think the most important thing is that the results are the same. So it would be a very bad idea, say, to change, to copy the source data just in order to have it independent of gap, and because that's asking for trouble. So I think,
Yeah,
especially
if you could guarantee that.
yeah.
Keep the same.
Yeah. So my opinion is it's very important to have one set of source data, and then as many systems as possible using these data. That would be the ideal world. So I think that
Also, I mean, these group libraries are not even called gap, they are gap packages. There's various different
yes,
authorships, licenses, whatever.
that's true.
Trick that.
Cool. Well, okay, that would be the fine print. Say copyright issues and such things. Yeah, I think. Well, this is a problem throughout OSCAR. Say.
It depends what you mean with track. So the manager, for example, says, well, if they transfer groups, it says the transfer groups library, and then it gives a citation to the bibliographic and so on.
Yeah.
But of course, if someone interactively accesses something, then it's the same problem even without the libraries, right? We doesn't use gap in the background, doesn't use polymath and so on, and insofar over with attribution. There's also a problem for Sage and so on. So
I know.
Trigger.
Cool. Yeah, I've had lots of discussions with the Sage people at the recommendation, which is roughly this. They discussed it with the gap people. Here I just see it. It's
So you have problems with that. Yeah. Yeah.
So if a new version of GAP is released and say it incorporates some bug fix or something in a particular function, is that automatically incorporated in Julia, or
No,
it has to be done manually by the Julia?
no. So the releases are independent. So if we have a new gap release, then the next version of OSCAR may try to get this new release, but it's not clear that this will actually happen. Yeah?
So any version of OSCAR uses a particular release. Can I say that this version of OSCAR uses GAP 4 something?
Exactly.
Yes.
Yeah, so that's what, because it's maybe sounded too negative, because too much was.
No, but not negative, but it's strict.
No, depending what you mean. So just it's important to say, the point is, so one aspect that is very important for us is the reproducibility of scientific results. This is the reproducibility prize is a topic in the national sciences, but beyond in general, right? So, and that's also something I did not touch upon this, which also has in focus, that you track very precisely all versions of everything you used. So the version of Julia, the version of GAP, the version of every single package being used. In pure GAP, this is not done very nicely because you can load GAP and two people may have both GAP 4.15.1, but they have slightly different sets of packages because someone installed a different version, then get slightly different results. And we try to follow the Julia philosophy here, which is to really record precisely which versions. So there's a manifest, it's called, created where you can really see the full log of this. So you see, was it the small groups library version 1.5 or version 1.5.1, which fits the match? And then, so that's why if there's a new GAP release, it's not automatically that your existing OSCAR version 1.5 will be automatically. OSCAR 1.5 has a specific GAP version. It's in there, probably 4.51 in this case. If 4.16 is released, all OSCAR releases will keep using this. However, of course, the person who makes the GAP release is me, and also the person who maintains the wrapper for GAP is me. So usually this is coordinated. So it's not like we make this release and then I'm like, oh my god, there's a new release. Oh, is it compatible? But rather we test this before, and then I make the release, and I'm pretty sure that it will be possible the next day to have this in the development version. It might take a couple more days simply because a lot of machinery is obviously compiled, blah blah blah. It's usually then in the development version very quickly, and then whenever the next OSCAR release is available.
One more point in order to stress what you said about GAP packages. So it would be really desirable to have a possibility to load GAP just with a prescribed list of versions of GAP packages. Just reproducibility is perhaps the most important issue. This then also has an effect to what am I testing? Yeah, so each different version of a GAP package may change test results. Perhaps even just some printed string got improved, and then suddenly one gets different result and has to explain. So it would be really good to have the possibility to tell GAP, well, here is my wish list for package versions, and load exactly these versions. If you have a better version, don't try, just then this package is not loadable at all, and in the end maybe OSCAR cannot be started because just the wrong package version for GAP. So this is something which is in a sense missing. Okay.
Thanks, and we have a half hour break. I lost track of time. Half 4, 5 till 6 is correct.
It's very quiet.
Before we ask this